So next talk is from Hao Huang. He is a PhD student from Ohio State University, and he will be talking about attack detection services in 5G. Yeah.
Thank you very much for the introduction, and welcome to my talk. Today I'm going to present 5G-Spector, the first ORAN-compliant Layer-3 cellular attack detection service. First of all, I would like to thank my collaborators, Phil, Vinod, and Ashish from SR International, as well as my advisor, Professor Zhiqiang Lin from OSU. First, let's review the evolution of cellular network. If we date back to the 1980s, we have the first generation of cellular network, which is usually for, just for voice communication with very, very low data rates. And gradually, if we move to the 1980s, we have the 2G, the second generation of network, where we can use a short message service for text communication, which is still prevalent in use today. And later, around the 2000s, we have the 3G network, and we started to have voice communication capabilities and also mobile internet access. And as we move to the 2010s, I believe most of us are very familiar with the 4G or the LTE network, where it offers a high speed of internet data, then we can have access to that everywhere. So as we move to 5G, so what actually 5G provides to us is the ultra high speed of data with extremely low latency. So this also enables tremendous opportunities of various applications, such as massive Internet of Things, AR and VR, etc. So why do we care about the security and privacy of 5G, or more generally, the cellular network? This originates from the cellular standard, which has been vulnerable since the legacy 2G or 3G standards. But unfortunately, this vulnerabilities still apply to the current 5G standard, or even very likely the future G networks as well. So this vulnerabilities actually allows attackers to exploit those messages to compromise the nearby base stations and the UE devices. So before explaining why 5G is not secure, let's first review a few terminology. Within a 5G network, there are the user equipments, which are typically known as the UEs. This broadly refers to your mobile devices, such as your mobile phones, your tablets, or other devices with cellular capabilities. There are also the base stations, such as the G0B in the 5G context, and also the mobile core as the backend, such as the 5G core. So before a UE establishes a connection and obtaining an IP address, it first needs to go through a number of procedures that are completely transparent to the users. And to begin with, the UE first starts a cell selection procedure, where the UE selects a nearby base station for connection. And then the UE follows a protocol called RRC to establish a stable connection with the base station. This is very similar to the three-way TCP handshake that we are very familiar with. And afterwards, the UE starts the NAS procedure, where the UE tries to authenticate itself to the mobile core and establish a secure channel so that the UE and the core can exchange data in a protected channel. So what can go wrong with this procedure? Actually, before the UE's authentication stage, the very initial messages transmitted between the UE, the base station, and the core, they are not encrypted and integrity protected. This further indicates that the attackers can exploit these vulnerabilities to easily eavesdrop, spoof, or flood these messages to compromise the base station and other user devices. So over the past few years, the mobile security community has identified several critical threat models to launch practical cellular attacks. For instance, adversary UE devices can flood Layer-3 messages to compromise nearby base stations as well as other devices. Man-in-the-middle attackers, such as rogue base stations, can sit between a legitimate user, between a base station and a UE, so that it is able to eavesdrop and manipulate the messages within the traffic. And more recently, it has been shown that signal injection attacks is possible, where the attackers can use radio devices to override legitimate signals within the traffic. And this can be viewed as a stealthy version of the man-in-the-middle attack, since the attacker only needs to transmit minimum signal power. Surprisingly, the cost to launch this attack for the attacker is very practical. And we show that normally an attacker only needs to purchase what we call a software-defined radio device, or an SDR, such as a USB B210. This can be further programmed with another portable device, such as your laptop or even a Raspberry Pi. The attacker can also run an open source software stack, such as OpenAir interface, that allows the attacker to instantiate malicious base station or UE devices. And attackers may also inject malicious code logic to implement practical cellular attacks in practice. So let's consider a few scenarios where the base station and the infrastructure or other devices can be attacked. Consider a mission-critical base station infrastructure where the base station is essentially connected to a few drones. And an evil SDR can launch distributed denial-of-service attack to disconnect the base station so that all the drones will be disconnected due to this attack. Another scenario is user location tracking, where a 5G user can be tracked if the attacker uses existing IMSI extraction or SUPI catcher attack. So the user's permanent identifier, such as the IMSI or the SUPI, will be exposed, and the user's location will be tracked around the city. So after reviewing these vulnerabilities and attacks, one natural thought is that can we simply fix the standard to eliminate all these attacks? So unfortunately, this is currently very challenging due to numerous concerns. So first of all, the cellular network standard is extremely complicated. And also, from a network operator's perspective, there are numerous concerns, such as backward compatibility, the performance, and overhead constraints that may affect the user experience. So how should we defend against these attacks without even touching the standard? So in this talk, I would like to highlight our insight on how we approach this problem. Actually, what 5G brings to us is not just the conventional bandwidth and network performance upgrade. It also enables a lot of new features and functionalities. Here, we would like to highlight one of the key innovations in 5G called the O-RAN. What O-RAN brings to us is that O-RAN allows not only network operators, but also security researchers and innovators to deploy and design security services on top of the traditional base station infrastructure. So what is O-RAN? O-RAN is also known as the Open Radio Access Network, or Open RAN. It represents a new software-defined open cellular network architecture. It was founded in 2018 by the O-RAN Alliance, and so far it has been adopted by 32 major mobile network operators in the world. So the key differences between Open RAN and a traditional network lies in the architecture's perspective. As we described before, a typical cellular network consists of the core network, the base station, and the user equipments. The base stations in a traditional network is something it's just a black box solution which is highly closed and vendor proprietary. With Open RAN, the base station architecture is broken down into different components that are interconnected with standardized and open interfaces. Another key innovation in Open RAN is the introduction of the control plane inspired by the software-defined network principle. This is realized by a centralized near real-time RAN intelligent controller, or the near real-time rig. The near real-time rig has installed multiple applications, as we call the xApps. These xApps can be different types of services, such as those network operators can use these xApps for monitoring or control functions so that the operators can do whatever he wants to monitor or control his network. So we can consider these xApps similar to the applications that we can install from our App Store, that we can install apps from our Android or iOS devices. And network operators can also download and install these kind of different services in the near real-time rig. Another key innovation in O-RAN is the introduction of the non-real-time rig that is handling high latency tasks. For instance, we can assume that machine learning models can be deployed on top of the non-real-time rig to support various security services, such as anomaly detection and other network performance optimization or traffic steering applications. So based on this architecture, O-RAN has several key capabilities over the traditional RAN. The first is the disaggregation because it essentially separates the control logic from the actual RAN implementation. And secondly, O-RAN offers modularization of the different services as xApps and rApps that are deployed on the controllers. O-RAN also enables different operators to participate in the RAN implementation with standardized and open interfaces. However, it is still not trivial to deploy and design security services on top of the O-RAN, and we have identified several critical challenges. The first is the visibility problem. Because the telemetry collected from the existing O-RAN service model, they are insufficient for security. Instead, they are mostly tailored only for network performance-oriented tasks. The second challenge is the extendability. With the evolving cellular attack community, there are more attack surfaces and types of attacks being discovered. So there is a need for an extensible framework to deal with not only current but also evolving attacks. The third is efficiency, which means the framework needs to have the capability to process data packets and produce real-time alerts. So we proposed the first ORAN compliance intrusion detection solution called 5G-Spector. 5G-Spector overcomes these three challenges with three key solutions. First, we introduced MOBIFLOW as a fine-grained type of telemetry stream that allows the network to collect UE state transition information and aggregated RAN statistics. Based on MOBIFLOW, 5G-Spector features a security xApp called MOBIEXPERT that works as a plug-and-play intrusion detection service on top of the new real-time rig. MOBIEXPERT uses the PBaaS programming framework that offers a decoupled architecture and an efficient IDS programming language. This is a high-level illustration of 5G-Spector's architecture, and I will break it down into different components. The first is about the RAN data plane, where we instantiate the LTE or 5G network with open-source UE and RAN implementation, such as OpenAI interface. We can either instantiate the network with either simulation or commodity SDRs, such as USRP. We further have another component of 5G-Spector, which is the control layer that consists of the SecSM agents. This agent is mainly responsible for the xApp registration and management, and also transmit and report the MOBIFLOW telemetry. This is instantiated and implemented through the SD-WAN project's owner's rig and deployed as a Kubernetes cloud-based environment. 5G-Spector further enables the MOBIEXPERT xApp that uses the PBaaS programming framework that allows network operators to easily integrate attack signatures and rules. And these rules will be triggered at runtime to produce runtime alerts to notify the network operators about the attacks. We further evaluate 5G-Spector with 7 different types of existing cellular attacks. We also try to derive different variants based on these attacks. So for all these attacks we simulated, we found that 5G-Spector can be written with different types of IDS signatures to effectively defend against these attacks. Here we will use one of the examples to illustrate how 5G-Spector actually works. Let's consider a BTS resource depletion attack, where an adversary user equipment tries to flood the base station with Layer-3 RRC and NAS messages. With 5G-Spector, the network operator can integrate PBaaS IDS signatures, and which will be deployed on top of the base station. At runtime, 5G-Spector's detection rule will automatically capture the attack flooding pattern within the real E traffic, so that the 5G-Spector xApp is able to produce a real-time alert informing the network operator about this attack. We further try to evaluate 5G-Spector in a real-world deployment scenario with over-the-air attacks. Here is our test environment, where we instantiate a 5G network testbed at the Computer Science Lab at SR International. We further present a live RF demo where we have a number of Android devices, and these devices are connected to the internet through a real 5G network. So for each of these UE, it will open a live Zoom session that allows these UEs to communicate through a live Zoom video. And then we launch using a Evo SDR to launch BTS resource depletion attack to attack the base station, so that all the user devices will be disconnected. This is a snapshot taken from our demo video. Actually, we have such a video available at our 5G-Sec website. I will post the link at the end of the presentation. It basically shows how the attack can be reproduced and how 5G-Spector is able to detect and produce an alert. So we further evaluate 5G-Spector with real-world datasets, and also we evaluate the performance and overhead. Due to the time limit, I will skip these details, and please refer to our paper. As for our future work, actually ORAN brings tremendous opportunities for security. So first of all, the introduction of the non-real-time rig enables security services with AI and machine learning solutions to be deployed on top of your network infrastructure. Secondly, ORAN also exposes a lot of new attack surfaces on the control plane, such as the malicious interfaces and the xApps that might be compromised by the external threat vectors. So there will be a need for us to deploy a zero-trust security framework to lock down the ORAN control plane to ensure it's free from any attacks. And further, as we have demonstrated the capability of 5G-Spector to detect the attacks in practice, it can be incorporated with the RAN data plane so that it can fulfill an automatic closed-loop countermeasure to fully mitigate this threat without any human intervention. So thank you all for your listening. If you want to learn more about our 5G security research, please visit our website at 5gsec.com. And we do have our 5G-Spector source code, artifact, and our video demo available all on our 5G-Sec website. So thanks again for listening, and I'm happy to take any questions.
Next speaker, any questions?
Yeah, I had a question. So I understand you have some kind of IDS. I was wondering the rules for the IDS. Do you manually generate them, or is it available? And for instance, if there is new attack schemes, how easy it is for your solution to also detect these?
So your question is the IDS rule-based extensible to future or
yeah, for instance, yeah.
Yes. So basically, yes, and here we demonstrated that actually it's possible. We have several attacks that we replicated from the existing literature, and then we also derived a few variants from those attacks, and then we confirmed that with the existing telemetry collected from our infrastructure, and our operators can still be able to write new rules to detect those attacks to extend 5G-Spector, basically.
Oh, okay, thanks.
Hanif Rahbari, Rochester Institute of Technology. So my question is about the resource exhaustion attack. And that has been a problem, a headache for cellular networks for perhaps a couple of decades. And 3GPP has trying to mitigate those attacks, like, perhaps, and not just 3GPP, but also research community on trying to do different types of maybe cryptographic techniques to authenticate who sends the messages, to reject those messages, and so on and so forth. So I'm just curious to know about, like, what are perhaps the limitations or perhaps the feasibility of these attacks given today's 5G network. In other words, are those rash attacks that you showed are the same as the old attacks, or they have been upgraded to still be feasible given the advancements in 5G?
Okay. So your first question is, what's the mitigation? How to mitigate these attacks, right?
Yeah, basically, I'm curious to know whether the 5G standard has done anything to prevent these old attacks.
So according to our knowledge, so for the attacks that we have replicated, like the BTS resource attack that we have implemented, the 5G new 5G standard does not eliminate this attack, and it is still possible to implement and reproduce this attack in a 5G network, and we have confirmed this is true. And I think most of the attacks that we have demonstrated, most of them are still applicable to 5G. But one of the fixed in 5G is like the encryption or the IMSI, which is encrypted to the SUKI. That partially addressed some of the attacks in the legacy standards.
Okay, thank you.
Any other questions?
Okay, thanks for the talk. So it looks like the proposed solution also could have a value in conventional 4G and 5G networks. So is there any reason focusing on the ORAN especially?
Oh, sorry.
So I think that the proposed solution could also have a value in 4G or 5G. And then is there any special reason to focusing on the ORAN specifically?
Yeah, I think, so ORAN is actually proposed in the 5G concepts. So yeah, I think it's agnostic to whether like 4G or 5G network you can do something about on LTE as well.
Okay, let's thank the speaker again.